All right, this video is going to be a review of how to find the discriminant. So if you recall, quadratics, if we put them in standard form, are written as ax squared plus bx plus c. We always make them equal 0. And for us to solve a quadratic, one of our options was to use the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And when you worked with the quadratic formula, there was something in there called the discriminant, and this part right here is the discriminant. So we have the discriminant is b squared minus 4ac. And if you can figure out what the discriminant is, it tells you some things about the problem. So today, in this video, we're going to look at the discriminant. Then after we practice with the discriminant a bit, we'll go back and we'll use the entire quadratic formula to find things. So this right here is important. There's our discriminant. So first, we're going to go ahead and look at the quadratic. So we're going to do some examples. We're going to look at the quadratic 3x squared plus 2x equals negative 5. So my first step is I have to make sure that this quadratic equals 0, and I'm going to do that by adding 5 to each side. So that leaves me with 3x squared plus 2x plus 5 equals 0. And then I'm going to identify what my a and my b and my c are. So here's a, here's b, and there's c. So my discriminant is b squared minus 4 times a times c. And when you do this problem, you can plug that straight into your calculator. It can look just like this. When I do that, I get negative 56 as my answer. So that means when I'm doing the quadratic formula, I am going to write negative b plus or minus the square root of negative 56. And when you look at that, you should say, well, that's a little bit weird. We're going to be doing plus or minus the square root of a negative number, and here on our calculator, we're going to get an error message. So that means that if we were to do the quadratic formula for this problem, we would get two solutions, two answers, one for the plus, one for the minus, but we get an error message. So we have two imaginary complex, and they call them roots because we took the square root to get the answer. So two imaginary complex roots. All right, so what we're going to remember is that if we get a negative number for our discriminant, we have two imaginary complex roots. And what this looks like, if you were to draw a picture of this, is this graph right here. So as you can see, the quadratic formula is used to find the x-intercept. And in this graph, we don't have an x-intercept. So that means when we use the formula to try to find one, we found an error message. We were like, well, that's not going to work because there are no x-intercepts. So here's the picture, and then this is what it means when we find this for our discriminant. All right, so that was example 1. Example 2. If we have the quadratic x squared minus 7x plus 6 equals 0, then that means that the a value is the number in front of x squared. Here I don't have a number. That does not mean that the number is 0. It means that the number is 1. There was a 1 there. So I have 1 for a, negative 7 for b, and 6 for c. So my discriminant is b squared minus 4 times a times c. And what I get here is 25 for my discriminant. 25. So if I think back to the quadratic formula, I know that I'm going to say plus minus the square root of my discriminant. So I've got plus minus the square root of my discriminant. So when I take the discriminant of this, I'm going to get two answers, one for plus, one for minus. And when I take the square root of 25, I do get real numbers. Those are not fake numbers. I'm not square rooting a negative. Those are real answers. And these real answers are nice. The square root of 25 is 5. When you get nice answers, they're not decimals that are weird. They're nice answers. Those are called rational. A rational number is one that can be written as a fraction. So these are nice numbers. The square root of 25 is 5. If I was to write that as a fraction, I would say that's 5 over 1. So I get two real rational roots. If I were to graph this problem, this is what it looks like. I can see that I have two x-intercepts, or two roots, and they actually cross at nice numbers. So that's what happens there. So my discriminant was a perfect square, and that gave me two really nice answers to find. So two real rational roots. All right, example 3. We could have the quadratic negative 10x minus 1 equals negative 7x squared. Again, I want to make this equal 0. In factoring, we typically want the x squared term to be positive. When we were doing the quadratic formula, we don't care. It doesn't matter. So I could take these and move them over here with this one if I wanted, or I could take this and move it over here with these if I wanted. Doesn't matter. I'm going to go ahead and add the x squared term over because I feel lazy. So I have 7x squared minus 10x minus 1 equals 0. And there's my a value, there's my b, there's my c. So the discriminant is b squared minus 4 times a times c. When I type that in my calculator looking just like this, I find that my discriminant is 128. So if I think back to my quadratic formula, I know that I'm going to be taking plus minus of the discriminant. So the plus minus means that I'm going to have two answers. I know my answers are going to be real because I really can square root that number. But this is not a perfect square, so that means when I square root this number, I get a nasty decimal answer. And whenever you get a decimal that cannot be written as a fraction, it's called irrational. So this is a crazy decimal answer, so it's irrational. Two real irrational roots. And here's what a picture of this looks like. You can see, again, there's still two x-intercepts, but if you look real close, you might see that they're in between numbers. They're going to be decimals this time. In fact, they're going to be decimals that are not nice. So the x-intercepts are going to show up. They're real. They're just going to be not nice decimals. So I'm going to write a little note to myself. Weird decimal answers. All right, and then last we have example 4. We're going to say we've got x squared plus 4 equals negative 4x. Again, I want it to equal 0. So I'm going to go ahead and add 4x to each side to make that happen. So I have x squared plus 4x plus 4 equals 0. So my a value is 1. My b value is 4. My c value is 4. And for my discriminant, I'm going to go ahead and say b squared minus 4 times a times c. Oh, I went ahead and set it equals 0. If you plug this in your calculator, you end up getting 16 for this part, and 16 for this part, and 16 minus 16 does equal 0. So I actually happened to write the right answer there. So when you have a discriminant of 0, you're going to be taking plus minus the square root of 0 when you do this. Now plus minus the square root of 0 is just 0. You don't get two different answers. You get positive 0 and negative 0. That's one answer. So here we're going to say that we have 1. Now the square root of 0, that's just a nice number. That means if you go back and you look, square rooting 0 means I'm just taking away that part. And so that means for me to find my x-intercept, I just have negative b over 2a. That's all I have. And so that means that when we find our x-intercepts, we're only going to have one of them, but it's going to be a nice one. It's going to be a number that can be written as a fraction. So I'm going to say I have one real rational root. And here's what that one is going to look like. In fact, that one real rational root we have is going to be the vertex. That's the only way for this parabola to only have one x-intercept instead of 0 or 2, as it must be the vertex right there.